Hi everyone, I'm Patrick, and in today's video we are going to learn how to get started with HuggingFace and the Transformers library. The HuggingFace Transformers library is probably the most popular NLP library in Python right now, and it can be combined directly with PyTorch or TensorFlow. It provides state-of-the-art natural language processing models and has a very clean API that makes it extremely simple to build powerful NLP pipelines. So today we have a first look at the library and build a sentiment classification algorithm. I show you some basic functions, and then we have a look at the model hub, and then I also show you how you can fine-tune your own model. So let's get started. Alright, so to get started, you should either install PyTorch or TensorFlow first, and then in order to install the Transformers library, you just have to say pip install transformers, or there's also a conda installation command that you can find on the installation page. So let's install it like this. So I already did this, and then we can start using this. So we can say from transformers, and then we import a pipeline as first thing and have a look at this. And then we also import some utilities that we need from the PyTorch library. So we import torch, and we import torch.nn.functional.sf. So we are going to use this later. And now we can start using this pipeline. So let's say classifier equals, and then we create a pipeline, and we need to specify the task that we want. So in this case, we want to do sentiment analysis. So we have to call it like this. And you will find the different available tasks on the website. So here we can see, for example, we have this sentiment analysis, which is just an alias of text classification. But for example, we also have a question answering pipeline, or a text generation, or a conversational pipeline. So yeah, this is how we can define a pipeline. And what a pipeline does is that it gives you a great and easy way to use model for inference, and it abstracts a lot of the things for you. So you will see what I mean in a moment. So now we can just use this classifier and classify some text by saying res for result equals, and then we call this classifier, and we want to classify a example text. So let me copy and paste some example text for you. So we want to classify, we are very happy to show you the smiley face transformers library. And then let's print the result and see how this looks like. So let's run the code. All right, and as you can see, we get the label is positive and the score is 0.99. So it's very confident that this is a positive sentence. And as you can see, it only takes 2 lines of code with this pipeline to create a sentiment analysis code. So yeah, this is exactly what we need. So we need to see the label of the text, if it's negative or positive, and we also get the score. So yeah, this is really nice. And now let's have a look at some more things that we can do with this pipeline. So first of all, we can put in more texts at once. So we can not just use one, so we can give it a list. So let's, for example, use a list, and then let's use another example text. So let me copy and paste this one in here as well. So we also want to classify this. We hope you don't hate it. And then we get multiple results back. So let's call this results. And then we can iterate over this. So we can say for result in results. And then we want to print the result. And now let's run this code and have a look at how this looks like. All right, and as you can see, for the second text, we get another result back. So here the label is negative and the score is maybe not that confident in this case. So this text might be a little bit confusing. We hope you don't hate it. But basically, this is how you can pass in multiple texts at once. And now, so right now we only use the default pipeline with the default model. But now let's have a look at how we can use a concrete model, and then also how you can use a concrete tokenizer. So what we can do is we can specify the model name and say model name equals, and in this case I use Distilbert base uncased and then fine-tuned SST2 English. So I will show you where I got this string or this name in a moment. But for now, yeah, this is basically just a Distilbert model, which is a smaller and faster version of BERT, but it was pre-trained on the same corpus. And then you see that it also was fine-tuned, and this is just the name of the dataset. So in this case, it's an English dataset from the Stanford Sentiment Tree Bank version 2. And yeah, so now if we have the model name, we can give this to our pipeline with the model argument. So we can say model equals, and then we use this model name. So now in this case, I can tell you that the default model for the sentiment analysis task is already this model name. So this should do exactly the same, but later we will switch this and then have a look at how we can use different models. So first of all, let's run this again and see that this is still the same. All right, so we see this is still the same result, so this worked. So now we just use this string to define our model, but now let's have a different approach to define a model and then also a tokenizer. So this will give us a little bit more flexibility later. So in order to do this, we want to say from transformers, and then here I import a auto tokenizer class and auto model for sequence classification. And this is just a generic class for a tokenizer. And this is also a generic class, but a little bit more specific. So in this case, I want to have it for sequence classification. And then it will give me a little bit more functionality specifically for this task. So don't worry about this right now. You can also find all the model classes available in the documentation. So if you're interested, then have a look at this. And also if you use TensorFlow, then here you have to say TF and then the name of this class. But the rest is actually the same. So yeah, this is how you use TensorFlow. And now after importing this, we can create 2 instances of this. So we can say model equals, and then we use this class, so auto model for sequence classification. And then we use a function that is called, so let's say dot from pre-trained, and then it also needs the model name. And we do the same with the tokenizer. So we say tokenizer equals the auto tokenizer dot from pre-trained, and then it needs the model name. So this dot from pre-trained function is a very important function in HuggingFace that you will see a lot. So you will see this later a few more times. So now that we created this, we can also just give the actual model and not just the string to the classifier or to the pipeline. So we can say our model equals our model and our tokenizer equals our tokenizer. So now if we run this, we should still get the same results because these are the default versions. And yeah, as we see, we still get the same result. But then later, if you want to use a different model or tokenizer, then you know how you can switch this. So just by using a different model and tokenizer here for the pipeline. So now instead of using this pipeline, let's see how we can use this model and tokenizer directly and do some of the steps manually. This will give you a little bit more flexibility. So down here, let's first use the tokenizer and see what this does. So first, let's call the tokenizer.tokenize function. So we say, let's call this tokens and then equals tokenizer.tokenize and then the string or the sentence we want to tokenize. So let's copy and paste this in here. And then once we get the tokens, we can use them and get the token IDs out of it. So we can say token IDs equals, and then we again use the tokenizer and the function convert tokenizer to, it's called IDs, and then it needs the tokens. So this is one way how to do this, or we can do this directly by saying token IDs equals, and then we call this tokenizer like a function, and then again we give it the same string here. So now let's print all these three variables to see where is the difference. So first we print the tokens, then we print the token IDs, and then here let's actually give this a different name. So let's call this input IDs. So now let's run this and see how this looks like. All right, so here is the result. So as you can see, when we call tokenizer.tokenize, then we get a list of strings, or the list of the words back. So now each word is a separate token. And for example, this one is our smiley face or our emoji. So yeah, this is what the tokenize function does. And then once we call this convert tokens to IDs, we get this one back. So now it converted each token to an ID. So each word has a very unique ID. And this is basically the mathematical representation or the numerical representation that our model then can understand. So this is what we get after this function. And if we call this tokenizer directly, then we get a dictionary back. And here we have the key input IDs, and we also have the attention mask. So for now, you don't really have to worry about this. But let's have a look at the input IDs. So if we compare the token IDs with the input IDs, then we see we have the exact same sequence of token IDs, but we also have this 101 and 102 token. And this is just the beginning of string and the end of string token, but basically it's the same. So yeah, this is the difference between these three functions, and then these input IDs. This is what we can pass to our model later to do the predictions manually. So now, like before, we can also use multiple sentences, of course, for our tokenizers. So for example, usually in your code, you have your training data. So let's say xtrain. And in this example, let's just use these two sentences. So this is our xtrain, and then we can pass this to our tokenizer, and let's call this batch. So this is our batch that we put into our model later. So we say batch equals tokenizer, and then we call this tokenizer directly with our training data. And then I also want to show you some useful arguments. So we say padding equals true, and we also say truncation equals true, and then we say max length equals 412, and we say return tensors equals, and then as a string pt for PyTorch. So this will ensure that all of our samples in our batch have the same length. So it will apply padding and truncation if necessary. And this is also important. So in this case, we want to have a PyTorch tensor returned directly. So I will show you later what's the difference if you don't use this. But for now, let's just use this. And then first of all, let's print this batch and see how this looks like. And then we get a dictionary, and again it has the key input IDs and the key attention mask, and then here it has two tensors. So the first one for the first sentence and the second one for the second sentence, and the same for the attention mask, so 2 tensors. So yeah, as I said, these input IDs are these unique IDs that our model can understand. So yeah, now we have this batch, and now we can pass this to our model. So let's do this manually and see how we can call our model. So in PyTorch, when we do inference, we also want to say with torch.noGrad. So this will disable the gradient tracking. I explained this in a lot of my tutorials, so you can just have a look at them if you want to learn more about this. And then we can call our model by saying outputs equals, and then we call the model, and then here we use 2 asterisks, and then we unpack this batch. So if you remember here, this is a dictionary, and here basically with this we just unpack these values in our dictionary. So for TensorFlow you don't do this, so you just pass in the batch like this, but for PyTorch you have to unpack this. And now we get the outputs of our model, so let's print the outputs. And as you might know, these are just the raw values. So to get the actual probabilities and the predictions, we can apply the softmax. So let's say predictions equals torch, or we also have this in f.softmax. And then here we say outputs.logits, and we want to do this along dimension equals 1. And let's also print the predictions. And then let's do one more thing. So let's also get the labels. So labels equals, and we just get this by taking the prediction with the index with the highest probability. So we get this by saying torch.argmax, and we can either put in the predictions or we can put in the outputs, and actually don't need this, but just for demonstration, let's use the predictions, and then again dimension equals 1. And then let's print the labels as well. And now let's actually do one more thing. So let's convert the labels by saying labels equals, and then we use list comprehension and call model.config.id to label, and then it needs the actual label ID, and then we iterate. So we say for label ID in labels to list. And now what this does, you will see this when we print this. So we print the labels. And now let's actually run this and see if this works. All right, so this worked. So as you can see, here we print the output. So these are our output. This is a sequence classifier output. And as you see, it has the logits argument. So that's why we used outputs.logits. And then we get the actual probabilities. And then to get the labels, we used argmax. So this is a tensor with the label 1 and the label 0. And then we converted each label to the actual class name, and then we get positive and negative. So by the way, this function I think is only dedicated to a auto model for sequence classification. For example, if we just used a auto model, then I think it won't be available. So that's what these more concrete classes will do for you. It gives you a little bit more functionality for the dedicated task. So we see that the loss is none in this case. So if you also want to have a loss that we want to inspect, then we can give the loss, or not the loss, but the labels argument to our model that it knows how to compute the loss. So we say labels, and then we create a torch.tensor by saying torch.tensor, and then as a list, we give it the labels 1 and 0. And now let's run this again, and then you should see that we should see a loss here. And yeah, now here we see the loss. And again, this labels argument is, I think, special to this auto model for sequence classification. So yeah, this worked. And now if we have a careful look at the probabilities. So first of all, we see we get label positive and negative. And here for the first one, this is the highest probability, so 9.997. And here for the second one, this is the largest number. So it took this one, and this is 5.30. So if we compare them with the results that we got from our pipeline, then we see these are exactly the same numbers. So now you might see what's the difference between a pipeline and using Tokenizer and model directly. So with the pipeline, we only need 2 lines of code, and then we actually get what we want. So we get the label and we get the score we are interested in. So this might be just fine. But then, yeah, if you want to do it manually, you can do it like I showed you, and you will get the same results that you can then use. So yeah, that's how you can use a model and a tokenizer. And yeah, so using the model and the tokenizer will be important when you, for example, want to fine-tune your model. So I will show you roughly how to do this later. But yeah, so this is how you use model and tokenizer. And let's just assume we did fine-tune our model. Then what we can do, we can say save directory and specify a directory. So let's call the folder saved. And then we can call tokenizer, and then we can call .save pre-trained, and then the location, just the save directory. And the same with our model. So we can say model.save pre-trained, save underscore pre-trained, and then again the save directory. And then we can load them in another application, for example, tokenizer equals, and then again here we use this auto tokenizer class, and then the from pre-trained, and then here we can give it a directory. So this from pre-trained, we can either give it a model name or we can give it this directory. And again, the same for the model. So model equals, and then we use this auto model for sequence classification dot from pre-trained, and then the save directory. So this should work, and then you should get the exact same model and tokenizer back. And yeah, as you might see, these these dot from pre-trained functions are very important, and you will use them a lot of time. All right, so I think these are the basic functions you need to build a pipeline or to apply the model and tokenizer manually. And now let's have a look at how we can use a different model. So like here, you can either load this from your disk if you already have a pre-trained model somewhere on your computer. But what you can also do is you can go to the HuggingFace Model Hub. So you can find this at huggingface.co/models. And here you have the Model Hub, and you can search through different models. So for example, you could filter for the tasks. So in this case, we want to do text classification, which is the same as sentiment analysis. And then it applies this filter. So you can see the most popular model is already this one. And then we can click on this and get some more information. And as you could see, so this is the exact same model name that we used in our code. So once you've decided for a model, you can click here and copy this name and then paste into your code. So let's say in this case we want to use a different model. So in this case I want to do sentiment classification with German sentences. So then of course I need one that is trained on German. So you can filter here, so you can search. So I can either again search for Distilbert and see what different versions there are available, or let me search for German. And then here, let's take the most popular one. So by Oliver Gur, and then we see this is a German sentiment bird, and then we get more information, and sometimes we also see some example code, which is helpful. So yeah, this is nice. And now what we have to do is we want to click here and copy. This will just copy the name. And then in our application, let me comment this out. And then let's again say model name equals, and now I hit paste. So now it pasted this string here. So now we have this, and now here we can give our model and tokenizer the model name. So model name and model name. And now let's do this for some example texts in German. So let me copy and paste this in here. So basically, let me quickly translate this for you. So this says, not a good result. This was unfair. This was not good, not as bad as expected. This was good, and she drives a green car. So basically, these three texts are negative. This one is rather positive, and this is neutral. So let's see if our model can detect this correctly. So now again, like above, we do the same steps. So we could copy and paste this. So let's copy and paste this. And then the same as above, we say with torch, torch.noGrad, and then we call the model. So we say outputs equals model, and then here we unpack our batch. Then we have the model, then we want to have the label IDs. So let's say label IDs equals, and then we use the torch.argmax function with the outputs and along dimension equals 1. And let me remove this one. And then we print the label IDs. So print the label IDs, and then we do the same as we do here. So we want to convert them to the actual label names by calling model.config ID to label, label ID for label in, here we call this label IDs to list, and then print the labels. And now let's run this, and actually let's also print the batch in this case, and let's have a look at how this looks like. So let's run this, and I get an error. So here I forgot to say outputs.logits like we did before. So let's try it again. And this is only 2 results. So of course here in our tokenizer we want to use these texts. So let's call this xtrain_German, and then let's use xtrain_German here, and let's run it again. All right, and as we can see, we get the labels 1, 1, 1, 0, 0, and 2, and this is equal to negative, 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 then 2 times positive, and then neutral. So yeah, this is exactly what I told you. The first 3 sentences are rather negative, then 2 positive ones, and this one is neutral. So yeah, now our German model works as well, and this is how we can use different models. So we simply search the model hub, and hopefully there is an already pre-trained version for the task we want. And then we can just use this here as our model name, and then we are good to go. Or if there is not a already pre-trained version, then we have to do this ourselves and fine-tune our own model. So I will show you how you do this in a moment. But now one more thing I want to mention. So I want to talk about this return tensors equals PT. So if we here we print the batch and here the input IDs, and then we see this is a tensor. So right now it's already in the PyTorch format. So we could use TensorFlow here, or we just omit this. And if we omit this, then we don't have this in the tensor format. So now it is just a Python list, I think. But then what you could do is you could convert this. So we can say batch equals, and then we convert this to a tensor by saying torch.tensor, and then we give it we call this batch, and this is a dictionary. So we can say batch and then access the key input IDs like we see here. And now we created a actual tensor out of this. And then we don't have to unpack it like this here. So now we remove this. And then if we run it again, then this should work as well. And yeah, this worked too, so we get the same result. And here we printed our batch, and now we see this is a tensor directly. So yeah, be careful here to specify what you want. So it's actually, if you use PyTorch, then it's just simpler to use this as a return argument. So return tensors equals pt. But if you don't use this, then you know what you can do otherwise. All right, so now we know how we can use different models. So yeah, try this out for other models in your language and see if this works. And now let's have another look at how we can fine-tune our own models. So this is very important. And I already prepared some code here, and I will go over this very roughly. But there's also a very great documentation about this. So we can go to this documentation page here, and you can also open this in Colab. So either with PyTorch or TensorFlow code. So this is really helpful. So I encourage you to check this out. But now let's go over this briefly. So basically there are 5 steps you have to do. So in this example, it's for PyTorch. So we have to prepare our data set, for example, load it from a CSV file or whatever. Then we have to load a pre-trained tokenizer and then call it with our data set. So then we get the encodings or the token IDs. Then we have to build a PyTorch dataset out of this with these encodings. So if you don't know what a PyTorch dataset is, then I will have a link for you here where I explain this. Then we also load a pre-trained model, and then we can either load a HuggingFace trainer and train it. So this abstracts away a lot of things. Or we can just use a native or normal PyTorch training pipeline like in our other PyTorch code. So yeah, this is what we have to do. So let's go over this very quickly. So in this case, we define our base model name. So we want to start with a Distilbert base uncased version. But in this case, for example, not the fine-tuned one, so just this one. Then step 1, we prepare the data set. So we write a helper function to create texts and labels out of the actual text. And here we downloaded some data set and put it in our folder. So I already did this here. And yeah, this is available at this website. And this contains movie reviews. So we want to fine tune our models on movie reviews for sentiment classification. So here we create training texts and the training labels with our helper function. And we also do a train test split to get validation texts and labels. And yeah, then as a next step, we create or we define a PyTorch dataset. So this inherits from PyTorch dataset. So torch utils data, we import dataset. And then we define this here. So again, I have a tutorial where I explain how this works. but basically it needs the encodings and the labels and it stores them in here. So yeah, this needs the encodings. So for the encodings, we need a tokenizer. So again, we use this from pre-trained function with the model name. And in this case, since we know we use the DistilBird one, we can use this class. So remember before we used a generic tokenizer, this auto tokenizer class. And here we use a more concrete one. So we use the DistilBird tokenizer fast. Then we apply it to training, validation, and test set and get the encodings. Then we put them in our dataset and create the PyTorch dataset. And then we import a trainer and the training argument. So this is available in Transformers library. And then we can set this up so we can create the arguments. So here, for example, we specify the number of training epochs, the output directory, the learning rate, and other parameters we want. And then we create our model, again from a concrete model class, and then with this dot from pre-trained function. And then we set up this trainer and give it the model and the training arguments, and then the training set and the validation set. And then we simply have to call trainer.train, and this will do all the training for us. And afterwards you can test it on your test data set, and then you have a fine-tuned model. So yeah, this is basically all you need. And then I also want to show you that instead of using this trainer, if you want to do it manually and have even more flexibility, you can just use a normal PyTorch training loop. So for this, we use a data loader and we need an optimization. So in this case, we use a optimizer from the Transformers library. And then here we specify our device. Then again, we create this model, we push it to the device and set it to training mode. Then we create a data loader and the optimizer. And then we do the typical training loop. So we say for epoch in num epochs and for batch in our training loader. And then we do the stuff we always do. We say optimize the zero grad. We also push it to the device if necessary. Then we call the model and we calculate the loss with this. And in this case, this is already contained in the output. So we can just access the loss like this. Then we call loss.backward and optimizer step and iterate. And afterwards we can set our model to evaluation mode again. And yeah, this is how we do it in native PyTorch code. And yeah, so this is basically how we do a fine-tuning and then can fine-tune our own models. And then afterwards you can also upload them to the HuggingFace model hub if you want. So yeah, I think that's pretty cool. And yeah, that's all that I wanted to show you for now. I think that's enough to get started with HuggingFace. And I hope you enjoyed this tutorial, and then I hope to see you in the next video. Bye.